All right. So here we go. You should be able to see that again.
Yep.
And good. I'm going to go back to that folder. All right. So after that great presentation by Sylvain, this is finally where we get to the point of presenting the actual code, which we decided to name BAM for a Bayesian assessment of model performance. Uh, because you want to compare both things and just say whoever you have sitting next to you, like, and bam, there it is. You can compare them both. So,
Okay.
uh, you like the name, so
I like the name.
yeah. Uh, so essentially, most of this background stuff we already covered in terms of the Jacquard similarity coefficient and the model precision and the model sensitivity, as well as the percent length ratio entails. But just to go into the code itself, well, this Python code, in order for it to work with, well, we intended for this code to be pretty seamless with Jupyter notebooks and with the whole Victor environment that we're all putting together. Um, it's meant to compute these Bayesian metrics to compare essentially two rasters. And although we intended the code to focus on flows in our scenario and volcanic mass flows, more specifically pyroclastic density currents, it can in reality be used for any sort of superficial features that you might generate through numerical models where you have an actual, let's say, true mapped or a true representation of that feature in real life, and then the actual output from a numerical model to compare it against. Um, so the foundation of this code comes from that Charbonnier et al. 2018 paper that we were showing during the presentation that was uh, uh, put together by Sylvain and Chuck, along with Laura as well, and Jacob Richardson. And then when I get into, let me see right here. Yeah, so basically the code begins by importing the necessary libraries. We will be using Rasterio, which we covered in one of the other um, lectures and one of the other meetings in the past, NumPy and primarily Matplotlib. So it's a pretty straightforward code in terms of the libraries that it's using. It's not using anything too complex, at least at this point in of the development. With Sylvan, we already have other ideas of things we want to implement and features we want to add to the code and in order to make it a bit more modular for users. And also what we were talking about in terms of implementing that weighted portion for the actual simulated flow, um, where we would be basically giving different weights to the cells because not all cells are created equal, as Chuck said. They will hold different values, so that should have some sort of impact rather than just being kind of a straight binary thing. So basically, the code you will give it two data sets. So you will give it your observed raster and then your simulated raster, and the code will read these. It will be actually able to extract the geographic coordinate system out of that, and which is important because later on we have it so it seamlessly implements that into the plots that it generates at the end. And that's the reason why we're using Rasterio. And then next we are actually computing these true positive, false negatives, and also look the length of the observed feature and the length of the simulated feature. For which this true positive is basically the number of the observed and simulated feature cells where are both positive, so greater than zero. Then for the false positive, it's going to be for the number of simulated feature cells that are positive, but the observed feature cells are not. And then the false negative is where the number of the observed features cells that are positive, but the simulated feature cells that are not. And for the length of the observed feature and also the length of the simulated feature, what the code is essentially doing is it's basically calculating the distance between the first cell that is detected when it's scanning from the top versus the last cell when it begins that sort of scanning from the bottom, and then it computes the distance between each of these, and it's going to do that for the observed raster, and it's going to do that as well for the simulated raster. Um, these are the basically the equations that you had already seen during the presentation, that I just included them as part of this document in order to make it easier, and you don't have to go refer the paper unless you want more details, of course. And um, finally, it just prints out the results for each of these metrics, and it generates a plot for each of them as well. So, well, not for the metrics themselves. Let me scratch that. It actually generates plots for the true positive, the false positive, and then the false negative. While the Jaccard similarity coefficient, the model precision, model sensitivity, and model percent ratio are actually printed as percentages. Um, Other than that, it's pretty straightforward. One important thing that we wanted to mention about this is how you have to first set up your raster before uploading it to Jupyter Notebooks or Victor here. For that, you would have to use something along the lines of GDAL Warp, um, which I did include a hyperlink giving some instructions on how to do this. It's kind of a simpler uh, instruction, method that it's giving by this website maps scaping.com. You can always also refer to the actual GDAL manual. But once you have both of these rasters match, then you can actually use the code, because the code will not clip those areas or crop those areas automatically for you. Maybe it is something that we could include, and I've been thinking about it in terms of having it be another code cell as part of this notebook. But for the moment being, you would have to do that externally, or you could implement that GDAL warp into this code. That's one of the advantages of these Jupyter notebooks, that you can take what we already have and kind of add things as you deem them necessary. Or the other option is you could always go the old school way and do this through ArcGIS or QGIS, for example. And then,
Just, just
mhm,
yeah. One
yeah,
more, one more thing you need to do is for your observed flow map. It needs to be a binary map with zeros outside of the flow area and number ones in the flow in the inundated area. Yeah, so you need to create that because when you take your outline of the flow area is just a polygon, right? So when you create the raster, you want to fill that polygon. So the inside of the polygon are gonna have number one values, and then the outside of the polygon is gonna be zeros.
mhm,
Mhm.
yeah, yeah, and that's only needed for
Yeah,
just for the observed feature raster. For your simulated one, you can keep that whole range of values that you
the
have
flow
for
depths.
the cells. Yeah, in this case for us, it's flow depths. Um, Now, you still have to make sure that the rest of them anything that it is outside, it is assigned to be a 0. So make sure that it's not that you have NaN values, non-existent values or anything of that sort. Make sure that you convert them to zeros if you don't have the output or of wherever you're getting your raster from to do that. Make sure that you at least reassign them to be zeros. And there are multiple ways of doing that. You can obviously do it through coding, but you could even use something as simple as ArcGIS once again if you wanted to set those up to be all zeros outside of your target areas. So I provided this one cell right here for anyone that doesn't already have Rasterio installed as part of their environment. Um, if you already have it, you don't need to do it again, but it's there just for simplicity, just so you don't have to look up how to do that. Pretty straightforward. And then this next portion is what actually gets into the code itself. So we have all of our libraries here on the top. And one feature I was going to mention um, that is that you might find it to be especially useful is that the code also allows you to assess a minimum threshold value for that simulated flow. Meaning if you don't want something to a portion of that simulated flow or those features to be considered, um, you can you can decide for the code to basically completely ignore that portion. The reason why we implemented this is because some of the numerical models that we're using with pyroclastic density currents tend to sometimes create a very thin layer of flow that in reality shouldn't be there. And it can be in the range of just like a fraction of a meter. Um, so we basically implemented this in order to have the code completely disregard any of those portions that are kind of I don't necessarily want to say a bug, but more so of a byproduct that was generated by certain numerical models out there. So uh, you don't have
A
to input the
feature.
number here.
It's a feature, not a bug.
It's a feature, not a bug. Yes, exactly. Uh, that one never gets solved. So it allows you to, yeah, like I said, input this minimum threshold. Now, you don't have to input it straight into the code as this portion. In this portion, all you're gonna do is basically press run, and you're gonna see it once we finally run this, that it will pop up here on the very bottom, and that's where you actually input that number. The one thing that you will manipulate in the code, and maybe I can also have it be sort of like a separate kind of pop up, um, a little. Yeah, I can definitely make it be a separate pop up blank that you're going to fill in. But for the time being, it's not. Is where you're actually going to input your two rasters. So this portion that says right here, your observed raster.tiff, you're going to replace that by your observed raster, still keeping the .tiff portion in the two apostrophes, and then you're going to do the exact same thing once again for your simulated raster in this portion. And then it goes through all these rasterio features that allows you to actually retain this coordinate system information, and therefore also ensure that these two will match once you're comparing them. Then this portion right here is actually what's applying this minimal threshold. And then it goes into the calculation of the area inundated by this by calculation of this true positive false positive, and false negative. Next portion actually calculates the Bayesian metrics that we were talking about, the Jaccard similarity coefficient, model precision, and model sensitivity. And then for the percent length ratio portion, it's actually doing what I already described, where it's basically starting from the top and basically goes through all these cells until it gets a hit in one of them, marks this portion, and then it does the same thing, but now starting from the bottom and until it gets a hit, and you're able to get this distance between both of them. It does the same thing for the simulated. And here is actually where it's calculating the distance for each, the observed and then the simulated flow. Once you have both of those, you can compute this ratio for compute the ratio for it's called the percent length ratio right over here. Pretty straightforward. It's actually following just a simple formula right there. Maybe I went too fast. Sorry, just showing it for one more second. And then you actually print out your results for the Jaccard similarity coefficient, model precision, model sensitivity, and the percent length ratio. This portion right here is just an implementation to actually update all of the axis values to actually showcase show the latitude and longitude in whatever coordinate system you have your code. Basically, your code metadata shows, because otherwise, which is what our original version of the code was doing, it was basically just showing pixel distances on each of the axes. So this is going to transform that to whatever coordinate system you're using. In our case, we're using UTM. So the axis will display UTM values for all of the plots. And then this is basically just gonna populate the plots. We're finally calling them right here. And then you have, well, this was updating the axes. This is actually converting those pixel to the geographic coordinates themselves. And then finally, you are creating, well, besides showing this true positive, the false positive, and the false negative plots, I also talked to Sylvain, and we decided it would be a good feature to have them actually output those as new rasters. So that way you may use those as layers, let's say, in any sort of if you want to visualize them or create a different sort of plot or go even further with your calculations, but just assessing just those individual rasters, may it be for that true positive, false positive, or false negative. The other reason why we did that is because, especially this one right here, you'll notice that it's a bit longer than the rest. And the reason for that is the way this one's coded is for the false positive raster to actually retain all of the values from that simulated flow, or for the simulated feature. So it will not be binary like the rest. It will actually retain the range of values that you had from your simulated flow or feature. The reason for that is then we can actually use those cells to go further with this code and implement this weighted Jaccard similarity coefficient idea that we're trying to move forward with.
That's really cool. Those are really amazing lines of code. I mean, it's really, I really like the way you implemented that. That's cool. It's very condensed.
Thank you.
Searching basically you're searching every pixel in the image, right?
Yes.
In the two tips. That's cool.
Yeah, precisely. Yeah, and thank you for that. I don't consider myself a developer or a programmer. I actually started learning Python with your class that I took when was this now? 2021. So it's been only about 2 years, but
Sorry
trying
about
to
that.
what's that?
Sorry about
Yeah.
Damn, I wonder how you did, man.
All right.
Yeah. So and then finally we plot this true positive, true false positive, and false negative rasters side by side. So, and this is right here at the end, it's where it actually is going to save the rasters. So at the end of the day, it's a pretty simple code, but it gets the job done. And the nice thing is that you will see it now once we run it, that it will output all of these plots right here on this bottom portion. The good thing about that is it will allow you to quickly assess your results, and then obviously you're still going to have these rasters populate in the same folder where you have your code. So if we take, for example, let's go with the first example here. You want to, any preference, Sylvain? Did you want to do Colima or Merapi first?
No, you can start with whatever.
Okay. So we'll start with Colima here. I'm just gonna replace that with this TIFF, and let's do
Molasses?
do molasses first. Okay, Chuck's favorite. Let's go for it. I haven't tested this one. This one's new, so let's see. All right, so now that we have that set up, hopefully I get no errors after the last few changes I made.
You always get errors after you make changes, man. It's the way it goes.
So we see right here on the bottom, it popped up this line saying, enter the minimum threshold value for the simulated feature. An important point to make about this, and I mean, I put it right here on where I wrote corresponds to the raster dimension in, for example, meters, which in our case is meters. Yeah, whatever value you input here, it's not a percentage. It will be actually, the threshold will be set for whatever dimensions your raster is in. In our case, if we write, let's say 1, it will mean that anything that has a thickness of 1 meter or less now will be 0. Same thing for 2, then anything 2 or less will be 0. Or rather, it will start considering from everything from 2 and above. Sorry, it's everything below 2 that will not be considered, not including 2. So we put that in there, and we're gonna do, okay, for this first run, let's just do 0 and see what happens. So just 0, enter, and it's gonna quickly populate with these plots. So it gives you, once again, whatever value you selected, it gives you the observed feature raster geographic coordinates. And I don't know why for the second one right now it's saying none. Okay, this is the new one.
Probably
So
I didn't set up the coordinate there. Yeah.
okay.
So
No
that's
worries.
correct. That's correct.
Okay, that's correct. Great. I was thinking, ooh, there's the error, but no, it's not. So
no, I think if you put the other ones, it's gonna show up.
Yes. And then it gives you your Jaccard similarity coefficient, your model precision, your model sensitivity, and finally your percent length ratio. Right here, you see the observed feature, or the observed flow in our case. That's what was mapped. That's what we said, that you need to set it up to be completely binary. So basically everything that you see in this very light blue portion is all 0. everything that has been mapped, may it be through a shapefile on ArcGIS, for example, it has to be set up to be 1. And then you have your
Declare
actual.
victory.
Hmm?
I declare victory.
Yes.
You only
You should.
feel
That's
it's
actually
victory.
pretty good.
Okay.
That's actually pretty good. So then you have your simulated feature popping up here. And then lastly, I put another one that in this scenario, they look exactly the same, just named limited simulated feature. It's essentially the same thing as the simulated one, but applying that threshold. So the nice thing about this is it will always allow you to quickly visualize what impact your minimum threshold that you set will have on that simulated raster. It's a nice way to be able to assess, oh, well, maybe that was a little too much, or maybe I could rerun this and increase this. Then the next two plots actually show that calculation for the observed feature length and the limited simulated feature length, calculating those distances between the first and the last pixel hits that we got from this. A nice byproduct of this, it's not really a bug, but I will still call it a feature, is it really allows you to see sometimes there will be some pixels that will be almost impossible for your eyes to discern, but the code is the code, so it will still pick it up. So sometimes it will seem like the flow starts here and all of a sudden you get like a random hit all the way up here, and you will be able to see that thanks to that through this distance calculator. So yeah, right now it is going in a straight line, so obviously this will have some effect in flows, for example, in this scenario, perfect case scenario, where it's actually bending quite a bit. So that's another feature that we have been talking about including next. It's actually what I'm currently working on, is to not only, I will still keep this automated kind of distance calculator, but we will also implement this a feature that will allow for the user to actually manually trace in a simple manner but efficient the flow for the simulated length and for the observed length, and then it will use the distances from that manually drawn distance for each. So then you will still have the automatic one if you so wish to use that, but you can also see what kind of impact that has when doing this sort of manually. In the library that I'm currently trying to do this with is called Tinker. And basically it will pop up a window for each of these, and you will just quickly draw a line on one, quickly draw a line on the other, and you will hit escape to exit both of the windows and basically continue moving forward with the computation. And finally, here are the three plots showing for the true positive, false positive, and false negative.
Man, it looks terrible now.
That allows you to see how these masters are, whether matching or disagreeing. And as you might have noticed, maybe not, but it ended up saving all three of these as new rasters right over here. So if I were to, let's say, I'm just going to quickly download this. I actually got to change my screen so you can see the, here, I'm going to stop sharing because I'm going to change the screen so you can see the entire desktop. Okay, so if I were to open this now, here you have your actual false positive raster, you see it completely removes all the other areas that we're not considering as part of this. So that means that the code is working properly.
That's
The way
cool.
it's intended to. Yep. And that's the first example. If we were to do the exact same thing now with, or rather, before we move forward with that, let me actually rerun this. And now I'm going to increase, actually, let me rerun it at, so we were getting what, 43.5%, 59, 61, 84. And now if I were to rerun this and I were to say,
0.1 put.
You want 0.1? We can do 0.1.
Which is 10 centimeter, which is
Yeah.
basically the threshold for these flows.
Yep, and it did have some effect. So
Mhm.
now we're getting 43.37, 60%, 61%, and about 84% for the next one. And you'll see that that basically if you want to see that effect of the distance right here, for example, if I were to increase this to 1 meter, there we go. See, it's basically shortening more and more the flow. So yeah, it's working as intended. Now, if we were to do the exact same thing with, let's say, Titan 2D, and we'll just run this again. I'm going to do 0. We see that
21%.
Yeah.
Terrible.
We see that the match isn't that great for this specific case scenario. And here's exactly what I was talking about earlier, how even though your eyes don't pick up that 1 pixel that's over there, it is there. So yeah, we were able to actually see that on the, was it, did we see it in the false positive? Yeah.
If you open the TIFF, you see it.
Yeah, it's not going to open it here though. I got to do the whole.
And it's a thin layer that is propagating upstream due to the mass discharge, the flux that is too high.
Mm-hmm. Yeah. I don't know if you can see it through Teams, maybe not, because it was, remember, we could barely see it.
Yeah.
No,
we cannot see it.
So
yeah.
Yeah, probably with the Teams resolution, you can. I kind of can. I mean, it's very, very, very faint.
Robert's got a question. He said or a comment. He said maybe you could add as an output a text file so you can save the different percentages as well, not just the rasters.
Yeah, that's a really good point.
Yeah, I already started implementing that as well. So it will save them all as a text file. So that way it's not like, I mean, that's the whole purpose of coding. I shouldn't have to take these, these percentages and have an Excel spreadsheet open on the other screen and having to, type in one by one.
Right.
It just doesn't make much sense. So yeah, that's coming along with the whole implementation of the manual distance for these. Yeah, but on this one, is this the one, Sylvain, that when we increased it a bit, it ended up matching a bit better? I think so. No.
Yeah, you can, yeah. But that's not, no, that's the Merapi one, actually. Because this one doesn't do a good job of channelizing the flow downstream.
Yeah, but it still went up from, what was it, 21% to 30% now, just by adding those 10 centimeters.
Yeah.
So, yeah. And now if we were to take, for example, bulk flow, let's see, there we go. All right, let's run this at 0. Get a pretty good match as well. It's a little low on the Jacquard. The rest seem fine. And this is one of those that it's pretty evident when you're looking at the that false positive raster, that you can see that it actually retains that range of values for the portions outside, and that will allow us to implement what we were talking about of this weighted Jacquard similarity coefficient. So that's one case scenario. Same thing with this one. Saw that if we increased it a bit, it was kind of getting rid of some of these.
Well, you don't have, in Workflow, you don't have too much of the thin layer spread.
Yeah.
So
it's very little. Yeah.
Actually, I think using the 0.
It actually, yeah,
not cutting it is better.
Yeah, wasn't it that we did? What was it though? 0.01 or something. That was.
Those for the Merapi case. That's only if you do.
Okay.
If you use Titan.
Yeah.
The Merapi case.
Okay, we can go to the Merapi now. Then observed. Now we're gonna do this one with this Dan 3D. Okay. And now we are looking at Merapi instead of Colima. And yeah, now this comparison is between the observed and Dan 3D, which I actually haven't used Dan 3D before. Sylvain, you generated this one.
Yeah. So it's a code that is using smooth particle hydrodynamics (SPH) as a numerical implementation. So it's a little bit different than Workflow and Titan. And so generally it's going to create a little bit more false positive, because even if you have some small mass that is going to be discretized by the smooth particle hydrodynamics method, it's going to go into other valleys, and then you can see that the flow is like actually going into several valleys instead of just one there. It's increasing the false positive, so that's decreasing your Jacquard fit and I guess your sensitivity.
Yeah. I mean, the sensitivity is pretty high. Yeah, the precision is pretty low. Yep. And if we were to compare that one versus, now let's go on Titan 2D. Quite different results.
Yeah.
For the two.
Better results with Titan.
Yeah, in this case, it's channelizing it better. You're getting less of that fanning.
Well, so it's an amazing tool, because you can immediately see, well, for some reason, bulk flow did a ton better on Colima, and Titan 2D basically didn't do such a great job, and then here at Merapi, it's doing a great job.
Exactly.
Yeah.
Does this give you insights into why that's happening, or I mean, is it?
I mean, kind of. I mean, I think in the Titan 2D case of Colima, I think it was mostly a problem of it's actually the way it's generating this grid on top of the DEM that is not seeing, the model is actually not seeing the valley. That is a pretty narrow valley. So
I see. Okay.
So it's spreading all the flow in the proximal area, and not seeing this valley that channelize the flow further downstream. And at Merapi is actually seeing it. So at Colima, we were using a higher resolution DEM. So maybe it just tells us that Titan 2D is doing well, like on some medium resolution DEM. But when you use a high resolution DEM, you got to be pretty careful that you got to smooth it out somehow. So then Titan can do a better job of seeing the valleys and channelizing the flows.
Yep.
So it's all about the numerical implementation and how all the model is actually spreading the flow from one pixel to the other.
But I mean, it's obvious with this tool, you're illustrating very quickly for us the point of needing to benchmark and calibrate basically in every situation.
Precisely.
Definitely. Yeah.
Yep. Yep. That's right.
So
Yeah.
what did you do here? Because
Now I
that's a
ran.
better.
Yeah. Now
That's a
this one
better
is
one.
VoltFlow
Oh yeah, okay.
at
That's
zero.
pretty much. Yeah.
Yeah.
Okay. Yeah.
Mhm.
But the model sensitivity is low. Yeah, that's what I. So it's creating a little bit more false negative actually.
Yep. Interesting.
Yeah, you see the false negative are pretty important there.
Mm-hmm.
Which is not good.
They're high. I mean, they're high on the volcano. So
yeah, they're high on the volcano, exactly. Yeah.
Yep. Yeah, so basically that's the code. I want to leave enough time for comments, questions, concerns, ideas, etc.
Thank you guys. That was awesome.
Yep. Thank you.
Thanks.
Do people have questions about this benchmarking story?
Just wanted to add a comment that you can use it for any flow model really, as long as you have a map or an inundation map of the observed, and then you have your simulation. You just have to make sure that the raster are aligned, perfectly aligned. They match in terms of the number of column and rows as well as the boundary coordinates. And then you have to make sure that your observed map is a binary file with like one inside the polygon number one values and outside zeros. But apart from that, it's pretty straightforward to use.
Yep. Yeah, that's cool. Very powerful.
Yep, and the nice thing is that we will continue developing this, adding more features, as we said, and yeah, it's pretty modular. So
yeah, but
overall,
I mean,
happy with it.
You know, if somebody was interested in like any problem, like if you go back to those diffusion models I was talking about a couple of weeks ago, you know, you could compare this with your gas flux data or whatever. I mean, you know, in terms of the map distribution.
Yeah.
In that case, you would have to choose a threshold that you care about, I guess. Like this is the anomalous gas flux. Does the area of my model, is the area of my model the same as the area observed, that sort of thing. It's nice tool.
Yep. Thank you. Yeah, and it's quite nice. Thank you for putting this class together, because it pushed me to write this, and it was actually initially Sylvain that had the idea, and he said, "Oh, well, you should write this for this class." And I said, "Well, we'll see."
Because I cannot write it, so that's why.
Well, I have to admit, you know, when you guys said you were going to do this, it's like, well, you know, that's great, but it's kind of boring. But you know, your code is making me excited about benchmarking.
Thank you.
It's such a cool result. I mean, it's like, wow, you know, that is neat.
Yeah.
All right, I'm going to stop recording because we're sliding into some sort of state.